This movie discusses the treatment of the 2D stationary heat transfer problem. It's totally analogous to the 1D stationary heat transfer problem. Of course, now we work in a plane instead of along a line. Each temperature point has two indices, I and J. We have to prescribe temperatures along lines, bottom line, top line, left line, right line, rather than at 2 points. Each temperature point ij has 4 neighbors instead of 2. It has a left neighbor, right neighbor, bottom neighbor, and top neighbor. Left neighbor I minus 1j, right neighbor I plus 1j, bottom neighbor ij minus 1, top neighbor ij plus 1. We look at this problem for finite differences. That means we have the stationary heat transfer equation and we replace the differential quotients by finite difference approximations. We know how to approximate the second order derivative for a single variable x. Now we have partial differential quotients, and the way you do that is that you keep the other variable y constant and then proceed just as in the case for 1D. This goes exactly the same for the discretization. Discretization is exactly the same as for the 1D case, except for the fact that we have to indicate that the second index is kept constant. The second index is j, which is constant in this expression. It always has the same value, and the I index varies from I minus 1 to I plus 1, just as for the 1D case. Second order derivative in the y direction, or the j direction, is totally analogous. In this case, we keep the I index constant, and we let the j index vary, j minus 1, j plus 1, and we divide by delta y squared instead of delta x squared. We also have a contribution from the source term, which is not relevant at this point. We write this equation in the ABCDE form. That's totally analogous to the ABC form for the 1D heat transfer problem. In this case, we put the coefficients of the respective temperature terms into variables A, B, C, D, E. I wrote down this form of the discretization over here. So we have A times Ti minus 1j plus B times Tij plus C times Ti plus 1j. That's almost like the 1D case for only variation in x direction, plus the bottom contribution, that's d times ij minus 1, plus the top contribution, that's e times Tij plus 1. And the values for these coefficients are k over delta x squared for A and C, k over delta y squared for D and E, and minus 2k over delta x squared minus 2k over delta y squared for B. How do we solve this kind of equation? It's totally analogous to the 1D case again. We use Jacobi. That means we bring all the terms except the central term with coefficient b to the right of the is sign, and we divide both sides by the coefficient b. The result is shown at the bottom of this sheet. And what we do next is that we say that the temperatures to the right of the is sign are considered to be at an old iteration level. So it says T it for all the temperatures to the right, and the temperature at the left is supposed to be at the new iteration level, at it plus 1. So what we do, we express the temperature at the new iteration level in point ij in terms of the temperatures of the neighbor point of the old or the former iteration. Remember, for one iteration in 1D we needed to have a loop over all points I. In this case we need a 2D loop, a loop over I in a loop over j to iterate over all points ij. In case we have a more difficult problem with non-constant delta x or delta y or non-constant k, it is advantageous not to use just variables a, b, c, d, e, but arrays a, b, c, d, e with index ij for all the coefficients a, b, c, d, e. For the rest, the treatment of the equation and the solution by Jacobi is exactly the same as on the former sheet. So here I indicated how to use Jacobi in case we put our coefficients in arrays. You might wonder if we can put the equations in a nice form in case we have constant delta x, delta y and k. This is indeed the case, but it is only a really nice form if the grid spacing delta x is exactly equal to the grid spacing delta y. I have indicated the ABC form of the heat transfer discretized equation over here. Below I have indicated the coefficients a, b, c, d, e. And suppose we multiply both sides of the equation by delta x squared over k, and we take delta x equal to delta y, then we find that all coefficients a, c, d, e become equal to 1. They're all multiplied by delta x squared over k, and delta x is equal to delta y. And our coefficient b becomes equal to -4. And if we then write the equation with the coefficients substituted, we find we have a coefficient 1 for all terms, except the central term with index I and j. It has coefficient -4. Very nicely looking, elegant form. Next we might wonder, just as for the 1D heat transfer problem, can we put our equation in the form of a matrix vector equation? We could do that for the 1D problem. We could write it as a matrix A times the temperature vector is a right-hand side. And we might also wonder, do we get a very nice form for the matrix for the case of constant k and constant delta x and delta y? And indeed, this is the case. But then we must find a way to put our temperature, which has two indices I and j, into a temperature vector which has only one index. This is done by numbering the temperatures in a consecutive way. We do it as follows. We start at the bottom row and we number the temperatures 1, 2, 3, 4, 5. Then we go to the next row and we number them 6, 7, 8, 9, 10, etc., 11, 12, 13, 14, 15. And in this order we can put the temperature in a 1D vector. So we have to map, as we express it, the 2D array for the temperature into a 1D vector. And this way we can do it. Note two things. If we have a temperature in a certain point, then the left neighbor has an index which is 1 less in the 1D vector. The next one, the right neighbor, has an index which is 1 larger than for the central point. How about the points at the bottom and at the top? Well, at the top I have to increase my index with 1, 2, 3, 4, 5 with respect to the index for my central point, and for the point at the bottom I have to decrease my index with 1, 2, 3, 4, 5. How does this work out if I look at the matrix? That's for the next sheet. I have my coefficients a, b and c. In the matrix the left neighbor and the right neighbor are just shifted over a distance of 1. That's just the same as in the 1D case. But if I'm going to look for my top neighbor, it shifted over 1, 2, 3, 4, 5. So I have to add 1, 5 to my index for the central coefficient to land up at the coefficient e for the top point. And on the other hand, if I want to know where the coefficient is for my bottom point, then I have to subtract 1, 2, 3, 4, 5 from the index for the central point. The points in between the bottom point and A, and the points between the right neighbor and the top point, they all contain zeros. So as you can see, the matrix contains an enormous amount of zeros. In case we have a simple problem with delta x is equal to delta y, and k is constant, and we multiply all equations by delta x squared over k, we get a really nicely looking matrix with as main diagonal -4, a subdiagonal with only ones, upper diagonal with only ones, and then shifted over a distance of 5 indices, we get another upper diagonal for the upper point, and shifted over a distance of 5, the lower diagonal representing the contribution from the bottom point. This concludes the movie about 2D stationary heat transfer.